Hi, my name is Anika Jena. I'm a researcher in Dr. Sho Takatori's lab in chemical engineering and materials, and I'll be talking to you about how viscoelastic deformation and dynamic swarms regulate the morphology and distribution of soft membrane domains in a polymer network and lipid condensate interfacial material. So first, I'll talk to you guys about my model system. So this on the left is what we call a giant unilamellar vesicle. In this case, giant, of course, refers to over 1 micron in diameter. So this is a three-dimensional spherical bilayer, which we electroform from 2 different types of lipids. One is a straight chain lipid and one is a kink chain lipid. And because it has these 2 different types of lipids, they relax to an equilibrium state, which involves phase separation. In the image on the left, you can see that the one phase is depicted in green and one is depicted just in black. So the green one is what we call the liquid ordered phase, which is a more densely packed phase full of the straight chain lipids, and the black section is what we call the liquid disordered phase, which is the kinked chain, more fluid section of the bilayer. So in order to make analysis of these spherical vesicles more doable, more easy, we can planarize it and bring it into a 2D morphology by splattering it onto a glass cover slip so that we can do planar geometry on it and analyze it easily under a microscope without having to use z-dimensional stacks. So then that you can see in the middle and the right-hand images. So the green dots that you see, which are gray in the middle, these correspond to the green condensed phase on the left-hand 3-dimensional image. And they're basically lipid condensates, like lipid rafts, that are floating around in this more fluid bulk. And so the reason that we are interested in this model is because it provides a very reductionist model of a cell membrane. So we don't have to worry about all of the macromolecules that are floating around on a live cell. If we want to study cell transport and phase separation in a cell system or a bio-inspired system, we can just use these lipids and electroform them into these bilayers. So next, what we want to add to our reductionist cell membrane model is a cytoskeleton. And so we do that using this very special polymer called actin. I'll be talking about that just right now. So here is actin. So this is filamentous actin. Actin is a polymer. It's called an active polymer, which means that under special chemical conditions, in this case, when you add ATP to the system, actin will produce its own internal forces and self-propel in these swarm-like formations, which are modeled by the Toner 2 equations, which were initially developed to model bird flocking, but it works for microscale stuff too. So we're able to electrostatically absorb actin to our bilayer because I didn't tell you guys before, but our bilayer is positively charged because we've inserted positively charged lipids, and actin, because of its amino acid sequence, it is a negatively charged polymer. So over here you see that these lipid rafts are being deformed into angular morphologies by the shear stress imparted by the actin filaments. In the previous slide, they were very circular, but now we start to see these angular morphologies as well as things like pinch-off events. Basically the structure of the membrane has been significantly changed by the presence of the actin. So I mentioned that actin is an active polymer, and that means that it will produce internally generated forces and swarm. So we can model this using experiment and theory. On the top, I have my collaborator Akanksha's theoretical work, where she's used the level set method to basically evolve a representation of our composite material over time. On the left-hand side up there, you see this weak convection model, which mostly consists of a little bit of activity, which is the swarming, and Brownian motion. On the right-hand side, that's right? Yeah. On the right-hand side, you can see a large amount of activity, so a lot of ATP, in theory, would be added to the system. On the bottom is experimental work. I'm an experimentalist. On the left to the right, you see that at high levels of ATP, there's this gyrating convective motion in the system, which is traced at the top by yellow and on the bottom by white. And it results in these very large, very deformed lipid rafts, lipid condensates, which have very strange morphologies and are quite large. So the reason, okay, good, shut up. So the reason that we are basically looking at the activity in these systems is we want to know what are the time scales at which this membrane model relaxes to equilibrium. So at the top, we see an active case and a passive case. So the active is this right-hand side strong convective model. And we see that at relatively very small timescales, the system will relax to equilibrium. Whereas in the passive case, the system takes much longer, if ever, to relax to an equilibrium state where it's not, where the domains have become large enough and coalesced enough to where it doesn't want to merge anymore. And we can also see the little diamonds on the top graph. Those are experimental data, and they corroborate, the experiment and theory corroborate each other quite well. At the bottom, this again is my collaborator Akanksha Gobela's work, guided by experiment. Yeah, we can see that at higher wave numbers, it takes much less time for the system to relax. And these graphs are the intermediate scattering function, which is basically a method for analyzing the motion of dynamic bodies. Okay. So that brings us to my latest project, which involves basically analyzing the actin network itself instead of the lipid condensates inside of it. So actin is a viscoelastic material, which means that it can exist in 3 phases. One is an unperturbed phase, where it's just, it's not being deformed in any way. The second is the elastic phase, which is modeled by that second diagram up there, second from the top. Actin is in pink, the domains are in green, and the green domains are pushing against the actin, but the actin is behaving elastically and basically snaps back to its original position. And then the third phase is when the actin network relaxes to a viscous phase and allows itself to deform as the domain pushes on it. So in the beginning, this was our hypothesis as to how we thought that the graph would look. In the beginning, we see the T to the 1/3 growth caused by Oswald ripening. Second, we believed that during the elastic phase, we would see no growth. And third, we would get a similar but slower trajectory, deformation trajectory of the actin to the Oswald ripening situation. Here we have what actually happens. So at the beginning, you can see, okay, here's the actin network, here are the domains, and here is a binarized version of the domains. Over here, first, we can see that the domains are smaller than the actin network. So there's not really any motion in the actin network, but I think just now, we can see that now the actin is kind of snapping back and forth. It's currently in its elastic phase. And then as time goes on, the actin starts to deform out of its initial position and turn into a different layout. It's basically now in its relaxed viscous phase. So yeah, that's a time lapse of many hours. So what we've found is that the initial hypothesis graph does not hold. So first, we do see the Oswald ripening, but then we see this interesting curve where the domain size increases. It looks like an it looks like an exponential increase on a log-log graph. So we think that maybe there are internal pressures that build up in these condensate droplets, which ultimately cause a large amount of growth over very, very long timescales. So yeah, thank you for being here and listening to my talk, and thanks to Dr. Sho Takatori and the whole Takatori lab for, hold on, there's something missing there, but that's fine. And thank you for the whole Takatori lab for supporting my work. Oh yeah, any questions?
Questions? Well, I have a question of my own at first. You said that, these actin network systems allow you to learn about cells in some manner. Could you speak a little bit more as to how, these studies are going to apply to things outside of the lab in the future?
Yeah, so one thing is that, so cells, if we look at it from a purely cellular standpoint, cells do undergo liquid-liquid phase separation, and the different domains that we see here have different transport properties. So we can kind of learn about how these sections evolve over time to know more about what molecules may be able to enter a cell, or how we can optimize drug delivery, things like that. There are also the concept of the actin network and cytoskeleton models are also very relevant to things like tissue engineering, where we want to synthetically create similar structures and understand how, for example, a cell will respond to being placed in a scaffold-like system. And then thirdly, because, as I mentioned, the different phases have different densities, different properties, different chemical properties, we can also think about creating a catalytic surface which has different catalytic properties on different sections of the surface. Yeah, does that answer your question?
Yeah, definitely. Thank you. Are there any other questions?
So you said when it goes to equilibrium, the actin network becomes elastic, and then it goes to, sorry, what?
Oh yeah, sorry, yeah.
And then it goes to viscous.
Yeah.
Does it ever return from viscous to the other forms?
So ultimately, we do not see that happen. However, one interesting thing is that this transition depends very much on how stiff the actin network is. So if you have a very stiff actin network, it can stay in the elastic phase for months, literally months, which is not possible to image.
You talked briefly about how you planarize the actin?
It's the whole membrane.
The whole membrane.
Yeah.
And I was wondering if you could talk about the process of doing that, and then why specifically you need to do that.
Yeah, sure. So if I go back to that slide, that was in the very beginning. So we have these vesicles, and doing three-dimensional math is hard. We also want to decrease the number of degrees of freedom which our system holds. So we don't want actin to, like domains, these lipid rafts, to be able to duck under the actin. We want to minimize that. So keeping it in a planar geometry helps with that as well. So how do we do that? I take a cover slip. I treat it with denatured heavy miramycin, which is a large protein, bulky protein, as well as I try and coat the glass, like chemically coat the glass with silane to make it more neutral, so that we don't get too strong adhesion between the positive bilayer and the negatively charged glass, because that wouldn't allow anything to move in the system, and we need these domains to be fluid. So basically, we just use gravity. I just drop the membranes onto a cover slip, which has been treated with silane, HMM, similar things, and the HMM forms a cushion, and just using gravity and surface tension, it just turns into that blob.
All right, well, why don't we thank our speaker one more time for kicking us off?